I would like to invite Professor George Haller to give his keynote lecture. Professor Haller from ETH is well known to all people involved with nonlinear dynamics, and so I don't think there is a need or also time to say many words about him. So please, George, give your talk, and please forgive me for this short presentation, but I prefer.
Thank you very much, Giuseppe, for the short introduction.
But it's better to give more space to you.
I appreciate that. Thank you very much. I'm George Haller. I would like to also thank for the opportunity. Thanks to Professor Walter LaCarbona for the opportunity to speak here. And in general, I think in the name of all the attendees, I'd like to express our gratitude for the great organization. This event has been organized fantastically so far. Everything on time, the information flow was perfect, and we all realized the challenges you and your team had to face. So we truly appreciate your service. This is a great service to the community. So thank you for that as well. So my title is Fast Reduction of Nonlinear Finite Element Models to Spectral Submanifolds. A long title. I'll spend some time on the details. I want to point out that a lot of this is joint work with my two extremely talented and hardworking postdocs, Shobit Jain and Mingwu Liu, who's, I apologize, I see I misspelled his last name already. So Li is the last name, Mingwu Li. I'm sorry about that. So I'll get back to his contributions later. It's just a quick sort of motivational slide that obviously these days complicated, complex, lightweight structures are the keyword. Everybody's trying to design such things. And whenever you go for a more energy efficient and more functional and more, generally speaking, lighter design, then you start inevitably facing nonlinearities. At the plane, there was a short movie running here that just stopped showing this plane which was clearly not intended to fly this way. And to understand better the vibrations that might be created by forcing, one would then go typically for a finite element model like that, right? And this is what my talk is all about. These models are incredibly high dimensional discretizations of the original problems. So they essentially lead, generally speaking, to ODEs of this form. Your classic mechanical system, ODE, generally with nonlinearities as well, and also with forcing. But the trick here is that X is a very large dimensional variable, as I showed here, and potentially you have multi-frequency forcing as well. So this might look like a standard MCK system, and which we all know well and teach well, but when N is really large dimensional and you have nonlinearities and forcing, this has remained a challenge really to solve efficiently. So once again, this is the key part here that I want to deal with. Because when you then try to go ahead and calculate forced response in the system, so what you see here is the classic diagram is how the system, a particular node in the system reacts to forcing. The horizontal axis is the forcing frequency, and the vertical axis is the amplitude of the forcing. Then we recover this classic forcing frequency response function. For linear systems, these are nice spikes without any hangovers, without any foldovers. So this is a very mildly nonlinear system, but as we all know, and what this conference is all about, is nonlinearities. So this would be the amplitude as a function, the response amplitude a function of the forcing, and this is the phase as a function of the forcing, right? So this is something we know well. Now, if you do this, however, in practice, I just want to show you an example where you do have nonlinearities as well. So this is a Timoshenko beam, just 21 degrees of freedom. We're not in the finite element domain, right? Far from that. It's a 42-dimensional phase space in which you want to do your simulation. And if you run a force response calculation, you try to find just the response of the system under periodic forcing, and you just use simple direct time integration for your system and say use your MATLAB code. The numerical time integration takes 21 hours. And you might ask why. because it's a strongly, the reasonably nonlinear system, very large dimensional phase space, and the damping is small, right? So it takes quite a while for the system to find the steady state, right? So, okay, there's no problem. There are codes that are specifically developed for this, right? One of them is harmonic balance. And I think we took in this paper, which we did in 2020, we took the best available code that we know of, the NLV code out of Stuttgart, and started trying to reconstruct just part of this force response curve. Again, what you see here is this is the forcing frequency, this is the forcing amplitudes, and the black bars were just the force response calculations obtained as a direct response to numerical simulation. This way only get the stable response, not the unstable ones. So then we used this NLV, and it took us 3 days, I'm not exaggerating here, just to get this part of the curve. And we're only in 21 degrees of freedom. Again, complicated nonlinear system. We don't know exactly what it is, light damping, and this is just for 10 harmonics, right? Then we took another approach, and then you can use the state-of-the-art continuation code that was already mentioned, COCO, which we use a lot. But it's, again, you're starting hitting the dimensional bounds of these products already at 42 dimensional phase spaces, 21 degrees of freedom, because this COCO calculation took 4 days, right? Just to get here. And COCO is fantastic. It can do a lot of things. It can do any system that you want, not just deep types of systems. But I just want to emphasize these problems are challenging, even with today's computational power. So this is why there's a lot of talk about model reduction, because we need lower dimensional models. Even this is too high to get even the force response. And this is the point where I wanted actually to start a calculation, if you allow me, to which I will come back later. But I just remember I started it now. This is a plate or shell problem. And I'll get to the details of how exactly that calculation is running. But remember, I started it now. But the calculation is all about, it's about this force response calculation on an iMac Pro in my office. It's a desktop. It's a 2D shallow curved shell. It's a two-dimensional problem, 11,000 degrees of freedom, which sounds like a lot of degrees of freedom compared to 21, but it's still nowhere near the finite element type challenges. Nevertheless, I want to show you in the end that this is now very very easy to handle with the technology that I'd like to describe. So model reduction. So how does model reduction work in general? There's a need for model reduction clearly, and it's concerned with this differential equation in general in the context of forced vibrations. And just to sort of discuss the subject, I neglect the nonlinearities for a second and the forcing. And again, we are in an n-dimensional phase space. The best to imagine what goes on with most model reduction approaches is to visualize that they are projections. And projections in the extended phase space of positions and velocities, basically most of the techniques that are out there and competing with each other envision projecting into modal subspaces. So say E1, so if you had, say, your lowest mode was a complex mode with oscillations, then in this R2n, the extended phase space of positions and velocities, this would be a two-dimensional subspace, right? You take the next mode, which is decaying faster, say, yet E2 is yet another two-dimensional subspace. The two together form a four-dimensional subspace. And you can add and add more and more subspaces that after, aligning the coordinates axes with the eigenvectors, they are even orthogonal to each other. And the philosophy is in a linear system first, that you take the full solution of the linear system shown in red, and you can understand that solution just by projecting it down to lower dimensional subspaces. If you want a four-dimensional reduced order model for a linear system, go ahead and project it down to the two fastest decaying modes, E1 and E2. If you just ultimately want a two-dimensional one, project it down, use the green one to the slowest decaying modes. And this works beautifully for a linear system because of the principle of superposition. However, people also apply this to nonlinear systems, and all the system, well, not all, but most of the model reduction procedures you see do just that. POD, Galerkin, and so on. They take a nonlinear trajectory, project it down to individual linear subspaces, and imagine and believe and hope that somehow from those projections, one can reconstruct the full nonlinear dynamics, even though these are no longer invariant. So that's the classic challenge. And that's why we have all these different methods that compete with each other and try to compare their errors on particular problems. And they work on one problem, not another. So what would be then perhaps a more general approach? I add now the nonlinearity and the forcing back. This is really a fundamental idea that I learned about not that long ago, but about maybe 10 years ago, but it was conceived in nonlinear dynamics literature right at the time when I was done with my PhD. And unbeknownst to me at the time, Steve Shaw and Christophe Pierre wrote this really amazing seminal paper about their idea that, you know what, maybe these linear structures here have nonlinear continuations, right? So then they started looking for them in terms of series expansions. In the mathematics literature, only about 10 years later, completely independently, you know, Rafael Della Liave and others didn't know about this work by Steve and Christophe, but they started looking at continuations of eigenspaces in the same fashion. So later came the mathematics. The idea here is that you take the same eigenmodes that you would normally have and try to look for nonlinear continuations of that. So this one-dimensional slowest eigenspace would have a nonlinear continuation here. I denoted by WE1. And I call this the spectral submanifold associated with E1, E1 being the spectral subspace that we started with. And I can also take this direct sum of E1 and E2, which remember was the slowest mode and the next mode, and try to look for a nonlinear continuation of that as a surface. And that would be the spectral submanifold W of E1 direct sum E2. And I can do this perhaps for each and every mode. Once I've added the forcing, I would also note that the theory is general enough that people have put forward to deal with that. And instead of just having an equilibrium there in the middle, all of a sudden you have an invariant torus there in the middle. The dimension of that torus is equal to the number of frequencies that you are using to force the system. So if you're forcing single frequency forcing, this is just a periodic orbit. If you have L frequencies, then it's an invariant torus of L dimensions. So the terminology would be this with the spectral submanifold associated with EK, which we call it. You don't see that term, you see N and M before, and that's still being used a lot. Why do we rename something which has already such a well-deserved name and everybody still uses it? Because unfortunately, the way it was imagined originally, it doesn't exist. Or maybe everything is an N and M. Indeed, near this equilibrium point or torus, when you try to compute these surfaces, it turns out there's infinitely many. In fact, the whole phase space is full of them. So to say that you're on a two-dimensional surface that's tangent to the eigenspace, you're not saying anything. Everything is on two-dimensional surfaces tangent to the eigenspace, like you would have near a node. So there had to be some more thought given to this, is that what exactly are we computing? Because what we're computing is true for all trajectories, right? So it turns out if you look into details of that, and you do some more work on the mathematical front, it turns out yet, yes, there are many of these surfaces, but there's a unique one which is smoother than everybody else. In fact, it's analytic. So when you're actually doing a Taylor expansion for high enough, one can specifically find the order for that, that's in the paper that I refer to here, then you actually place yourself on that unique one. And that's the one, that's the spectral submanifold, and that's how we differ from N and M. This is the unique, if you will, N and M, that's the smoothness, because there's many of them. You also have several conditions that need to be satisfied, non-resonance and smoothness. Anyway, so the theory is in good shape, with that I would say. And here comes the idea, model reduction is no longer experimenting with projections and hoping that even though those are non-invariant, they give you the right result. It's restriction to these invariant manifolds, which works in any dimension. So your phase space might be 100,000 dimensional, but these manifolds under the appropriate conditions are there and they're unique, and let's find them and reduce to them. If you do this calculation, just to the simplest example that Pierre and Shaw had, this is two nonlinear oscillators. This is from their paper. We, I think, modified it slightly in these publications just to show them. This is what actually happens there. See, so this is the computation of, or after cleaning up the details and yes, uniqueness, you have a flying carpet there because this is a forced problem. And that flying carpet is the SSM, the spectral submanifold, the slowest, attached to this periodic orbit that you see here. Okay, that's the primary force response. And any bifurcation, anything else takes place on this flying carpet, on this periodically moving carpet. So it's worth investing, computing this and reducing to your mechanical system into this. In fact, the reduced order model can be computed in appropriate coordinates explicitly. And by hand, SSM2 was the first code, FSM21 computing these. But by hand, in fact, for this problem, you can make analytic predictions for things that were not accessible before. Isola merger, right? You can predict that analytically and not without any numerical simulation. This is an analytically predicted value for the existence and for the bifurcation of an isola that continuation codes would have a hard time finding. So it's an amazing tool to use these spectral submanifolds. So why isn't everybody using them? Well, how do you compute them? That's the question. Well, here's a spectral subspace over which you're looking for to find a tangent invariant manifold for this problem. So the first thing you do, you turn it into a first order problem. That's what everybody has been doing. Steve Shaw, Christophe Pierre, and also in the math literature, Rafael Della-Davia and others. So you introduce a 2n-dimensional phase space of positions and velocities. And then in these nice coordinates, you look for a graph over this invariant subspace after you have aligned your coordinates with the subspace. So basically, once you have transferred your first two coordinates to align with the spectral subspace, you also diagonalize the linear part. So after a linear transformation, you have a new 2n-dimensional system of differential equations where this is diagonal, and this is the nonlinearity, and it's also time dependent, so it's the diagonal matrix. And these are good coordinates. This is how we also teach center manifold calculations. Why not go with them? There's a slight problem. In fact, there's a big problem. To achieve this form, to achieve this diagonal linear part, you need all the eigenmodes of the problem. And we're talking about a finite element setting. We are talking about hundreds of thousands, if not millions of modes, which are unrealistic to compute or even store. And even more alarmingly, by doing this transformation, you destroy the sparsity of the nonlinearity that you naturally had to begin with, because only the nearest neighbors would interact with each other in finite elements. So you're creating havoc just by getting good coordinates. You're creating a bad setup for the calculation. Just for you to appreciate these problems, on a finite element mesh that Shobit calculated this on for a von Karman type shell. If this is the number of degrees of freedom, and this is the the storage required for computing all eigenvectors, it goes up exponentially in this logarithm. He couldn't even compute them, for these values, 10 to the 5. This is still below or at finite element grade. So if you just calculate the first few eigenvectors, you're still order 1 in terms of storage. That's manageable. But to compute all eigenvectors, it's unfeasible. It cannot be done with today's computing facility. Capacity. The time is even more alarming. The number of degrees of freedom, only up to 10 to the 5. The computation time, just to compute the eigenvectors, you're not doing any nonlinear analysis, would be at this level 10 to the 5 a year. And this is on a fast core, fast cores on the cluster. So this is unrealistic. So the burden that the diagonalization imposes on us it cannot be handled. The other thing is the destruction of sparsity. In original physical coordinates, the nonlinearity, which is sort of a tensor that stores all the coefficients of nonlinearity, is nice and sparse. But with that modal transformation that puts you in diagonal force, you make it full. And as a result of that, with the phase space dimensionality, again, say going up to 1 million, the storage space that you would need for this transform nonlinearity, say at order 2 already, quadratic, but at cubic is 10 to the 10. This is gigabytes, right? And 10 to the 20 if you wanted to order 5. At the same time, if you left it in original coordinates and you didn't transfer them, then you would have very manageable times. And so therefore, this problem, even though it's beautiful, the setting, it was unmanageable. It has been unmanageable. We've been writing papers about it, pushing the boundaries of this, right, further and further. But at some point, we bumped into these unavoidable obstacles. So then we were scratching our heads what to do. So there came the idea is then, well, can we just avoid this transformation at all? Even though all invariant manifold calculations start with that. Can we do it without that, right? So it's the same problem. And we, again, introduce these coordinates and we are now in the extended phase space of positions and velocities, right? But, and you will have a coefficient matrix which is the mass matrix here. And this is the z, x dot. And also I'm introducing phases for the forcing frequencies here. So phi dot is omega. We have L forcing frequencies, a fairly general forcing with L harmonics, right? L can be anything. So this can model pretty complicated forcing. But we're not gonna invert B either, and we're not gonna diagonalize A, but rather we're gonna be looking for an invariant manifold using the parametrization method that was developed in a more abstract setting for mappings on Banach spaces by Della-Davia and co-workers, right? And say the following: whatever the invariant manifold is, instead of changing coordinates, we'll look for it as a function, as an embedding from some parameter space, P, and also dependence on phi. So there's an abstract space, parameter space, that intrinsically parameterizes these manifolds rather than trying to construct it as a graph over the eigenspace, okay? So there's no diagonalization needed. And also we look to construct the dynamics in that parametrization space, and the right-hand side of the dynamics is unknown at this point, and we will try to pick it as simple as possible, basically a normal form approach. And when you then take these two functional forms, first you need to know that the SSM exists, but we know under certain conditions, and you basically differentiate this the first relationship in time, then you start getting a differential equation for these quantities, and then using the invariance of this manifold, as usual, this leads to a PD, or called the cohomological equation, which then we want to solve for these equations. But mind you, we never changed coordinates. This will be now harder to solve because there was a reason why we were all changing coordinates for the proofs and the constructions. None of these matrices are diagonal, resonances are not easy to diagnose, and so on. So it comes with a lot of challenges, and Shobit is going to go into that in another talk. But principally, again, you look for the solutions in terms of a combined Taylor Fourier expansion, or you also need the Fourier expansion because you have forcing frequencies. You plug these in and you get a bunch of equations which you need to solve. They're linear equations, as if you were doing Taylor approximation. So in the end, when you work this through, and it's a lot of work, then you can solve for this now for any nonlinearity and any forcing. It's a recursive algorithm. And this only involves, when you work it out, the master modes. So if you want to construct a 2 or 4 dimensional SSM, you only need to then use the 2 or 4 eigenvectors corresponding to that, rather than the 500,000. Major simplification and that major reduction in computational time. And we can now do spectral submanifold calculations of any order in any dimension. Of course, it's going to take more and more time, but it is doable. It's just really just taking more and more time. You've seen the memory and computational time graphs, and we can detect resonances automatically. This actually results in several orders of magnitude reduction. And then all these problems that were not manageable to this approach before become within reach. So there's now there's a code that we just released a few days ago. It's SSM Tool 2.0. It computes SSMs using spectral submanifolds. Using this approach, this is open source. It's MATLAB-based live script. That's what I started running at the beginning of this talk. I get to that in a second. And what it has, actually, it has a generic finite element code integrated in it. So the finite element code provides these nonlinear coefficients for the actual SSM computational tool. It then computes SSMs of arbitrary dimension and order, and for arbitrary forcing as well. And it handles resonances. So whenever you have resonant modes, then automatically it will not be a 2-dimensional SSM, but it will be a 4-dimensional, 6-dimensional, because you want to include the resonance modes. That's also built into the code. And I already mentioned COCO. COCO is incredibly helpful and useful. So once you do have a rigorous model reduction, we can use COCO to explore that 4 or 6 or 8-dimensional system and find, say, 2-dimensional tori or 3-dimensional tori in a 500,000 dimensional phase space, which was, it was unattainable before. But with this intermediate step of getting to the SSM, COCO can be deployed. And Mingwu is an expert on COCO. He participated in development so that he integrated into this package. So there's several papers coming out of this, and I just show you a screenshot of how this code works. So anybody can take this and modify the script to include their example. In fact, I want to check if I'm done with the computation, which is, as in good tradition, it gives me an error message, right? So I ran it right before I started this. It ran. So anyway, it takes about, I don't know why it stopped, but
we believe you again.
But anyway, I just go back to the talk. The point being is that it solves this like real time about 10 minutes. I just got this version. It ran before the talk. Anyway, so I've been there. This is the type of, for instance, one example. But let's go to a particular example because I need to get this finished. This is a wing problem, right? So it's an airfoil problem that Shobit worked out. The number of elements in this finite element method is practically 50,000. The corresponding degrees of freedom are 135,000, okay? I presented you with the difficulties for 21 degrees of freedom or whatever at the beginning, right? Already, it was incredible computational cost to get the exact force response. This is now dimensionalized 270,000 dimensional phase space, okay? So instead of experimenting with projections, this code computes these invariant manifolds exactly, reduces the dynamics to them. And if there's no resonance, that invariant manifold is two-dimensional. On that one, without any simulation, you can find the force response as an appropriate fixed point, because you can factor out the rotational degree of freedom in all these problems when you use polar coordinates in normal forms. So the mesh assembly was 1 hour and 21 minutes, which can be improved because we are not, professional finite element developers, although this is Shobit's code and he's done a great job, but this can be further optimized. But the actual SSM calculation at order 3, 11, and that's what I wanted to show you on a simple problem, 11 minutes, at order 5, 35 minutes, and order 7, 44 minutes for this number of degrees of freedom. So you get this, within minutes, and it does show you that this is a simulation-free calculation of the force response, because once you have the SSM, you just find the joint zero set of two functions, and that's your force response. And it shows that the third order reduction wasn't quite great, so you have to go up to order 5, and then when you go up to order 7, then there's no fundamental change. So this actually, unlike previous perturbation methods that give you one answer, a one-shot answer, and that's what you have to live with, here you can set the order of the expansion for the SSM up to any point and decide whether you have converged or not, okay? This is another example by Ming-Woo Lee. He looked at this plate example, square plate, and this is a 1-1 resonance because of the geometry, okay? And then when you run this, it ran up to 200, he did this for 240,000 degrees of freedom. That's a 500,000 dimensional phase space that still took less than a day to run. Again, we're talking about 500,000 degrees of dimensions. And then you get as an output the force response curve, again, near the first frequency. The dotted one is the linear. The red one is the order 3 calculation. Order 5 doesn't differ much. So basically, that's justification that you actually, in this particular problem, you could have stopped there. COCO is integrated. So at these points of loss of stability in the force response, COCO can take care of finding, say, Hopf bifurcations in that case. So this is a magnified image of those Hopf bifurcations. And what you have is a torus branch bifurcating out of the main force response. Okay, some of it is stable, some of it is unstable. So what you see here, just to appreciate, this is a 2-dimensional invariant torus in a 4,082 dimensional phase space. So he did it for this second one, but only because he wanted to verify it numerically. The thing to understand is that the computational effort, once you have the SSM, is the same in 2,000 degrees of freedom and 240,000 degrees of freedom, because you have reduced to an invariant manifold of the same dimension. It makes then no difference, right? It takes longer to compute the invariant manifold, but you can find the torus just the same. But this is already almost 5,000 dimensional phase space and invariant 2 torus. So I was very impressed with that, and we really needed the expertise that Ming-Woo has with COCO. A summary. So I just wanted to say that SSM theory is a reduction of the force nonlinear system, in fact, any force nonlinear system, to a unique low-dimensional invariant manifold, okay? And with these new advances, this has sort of stepped out of just of its academic beauty and has become directly applicable to very high-dimensional systems of finite element grade. And so it can meet that challenge, right? And Shobit will talk more about the details of that in this reduced order model session on Thursday, which I think I'm chairing, so at 5:15, okay? So SSM2, this code that does that, this is a free open source code, and it can handle nonlinearity of any order and type, general linear nonlinear damping, multidimensional SSM resonances. Many of our colleagues here kept asking me for years about, so okay, but what about resonances? So I'm pleased to say that we can have internal resonances and bifurcations now handled. This is a 3-dimensional torus in one of these calculations that's living in a very high dimensional phase space. And we can get that now for finite element problems. So I was incredibly pleased to see that. I have to say, just a few days ago, we found a very nice preprint on archive.org, which does the same thing, about the same thing from a normal form perspective, but in the end actually also calculates the spectral submanifold. It does have limitations compared to what we're doing, because it can only do cubic approximation. It can only handle geometric nonlinearities, Rayleigh damping. It has an autonomous approximations. However, at the same time, the authors took a lot of time to calculate at least the third order formulas by hand, which I think is very, very helpful. And it's also they showed that one can do this in a non-intrusive way. The third order coefficients also we can get in a non-intrusive way. Problem comes when you have 5 and 7th and higher order, then you have to have this recursive algorithm. I think there will be talks also related to this in the workshop, potentially in the same session. I wanted to, I don't see from the titles, but presumably. There's an ongoing extension of these two data-driven problems. So what if you don't have the equations? You can still try and construct these invariant manifolds in the phase space and come and become and obtain lower dimensional reduced order models. And a PhD student from my group, Mattia, will talk about that in another session on Wednesday on the reduced order model 1 session. And that would be my talk. Thank you for your attention.
Thank you. Hello, George. Can you, thank you very much for your extremely interesting talk. The problem of a reliable dimension reduction for dealing with high dimensional mechanical systems in nonlinear dynamics terms is extremely important, is the future, maybe one of the future issues of nonlinear dynamics in view of applications to high dimensional systems. And it seems that you are doing an excellent, you and your group are doing an excellent work in terms of mathematical basis and computational efficiency for describing everything on these invariant manifold. So
there are questions, Giuseppe, in the QA. So there is a question by RT.
Okay.
I'm wondering, can the method handle the non-smooth nonlinearities as well? You can read the Q&A, please.
That's a good. May I answer that? Right.
Yes, please.
So right at the point where these manifolds are constructed at the expansions, right at the point of expansion, you cannot have any non-smoothness. Otherwise, you cannot differentiate the manifold, right? But away from it, yes, no question. I mean, what it will produce is it will produce higher order expansions that try to approximate any potential jump in the manifold. But what it's absolutely crucial is that you should have smoothness right, say, near that equilibrium point. If you hit something later, then that's not such a major challenge. We can also just approximate that constraint with a very steep function. I have to admit we haven't worked that out, but I see no conceptual problem there, only non-smoothness at the equilibrium point.
Okay, we have, Giuseppe, can you read or shall I read?
No.
Or shall I read to make it?
You can also, if you see it, we have a lot of questions by Americo.
So there's a second question by Americo Cunha. Sorry if I mispronounced the name. Thank you. So 2 questions. Could you comment about the similarities and differences between the reduced order models obtained with submanifolds and those computed with machine learning tools like cringing, polynomial chaos, neural networks? What are the advantages of your approach? Machine learning tools, which we're also using, are guessing about the existence of these, right? They don't know. We have an exact theory that tells you that they exist. They also give you cases in which they don't exist, so don't bother, right? So you can still run a machine learning algorithm that will probably produce something approximate even when it doesn't exist. So the value here is that we're reaching speeds that we don't have to rely on machine learning. We get the exact thing, right? And for those of you who have worked with machine learning, I don't have to tell you that that's a major advantage, but then you don't have to change methods and try hypersensitivity dependence and parameters. These are exact formulas. So that's where I see the approach, right? Same classical reductions, POD, Galerkin. People are writing papers about POD and Galerkin because they don't universally work. You're projecting down to a subspace which is not invariant. You're cutting it off, pretending that it's invariant. It's not. The solutions from that just projected subspace leave, right? So in some cases, when you're close to the origin, you will be lucky. In other cases, you won't. You never know in advance until you have actually done the work. And to refine POD and others, you have to increase the number of modes, the dimension. To refine SSM, you don't. The dimension remains the same. You just increase your order for approximation and get better and better approximation for the invariant manifold.